Okay, thanks, Sumit. All right, thanks for making it out on Monday afternoon after what was quite a long and dense week last week, where all of you and many others were. So yeah, we've been working a lot recently with AJ, and also AJ and I have been working independently on various multi-level Monte Carlo methods in an inference context. There hasn't been an enormous amount of work in this area, and a lot of what's been done has been done by us. And so in this talk, I'm going to tell you in a bit of detail about this multi-level sequential Monte Carlo samplers, which is the first example of these MLMC methods for inference that we did together with AJ. And then I'm going to sort of survey various other methods that we've worked on together. And so this is why I've put others here. It's not that any of our other collaborators are any less important, but there are so many that they wouldn't fit on this slide, so I'm going to acknowledge them as we go. In particular, the original multi-level SMC samplers is with Tampone, Beskos, and Yanju as well. And we had some follow-up work on that with Pierre Delmorand. Okay, so I'll introduce the problem. I'll spend a bit of time telling you about MLMC sampling at a very basic, a very pedagogical level. Then I'll introduce the Bayesian inverse problem that we're going to consider here. And that will contextualize these SMC samplers, and in particular the MLSMC samplers. And then I'll tell you about some other algorithms that we've worked on which can fit into any one of these three bins. So all of the various methods that have been all of the various methods that have been introduced can fall into one of these three categories of either an importance sampling strategy, a coupled algorithm strategy, or an approximate coupling strategy. MLSMC samplers, that's what we're calling a importance sampling strategy. A coupled algorithm strategy are including things like, so another algorithm that fits in here, if anyone's familiar with that, is the original multi-level Markov chain Monte Carlo by Stewart, Schwab, and Huang. Around the same time, there was a multi-level Markov chain Monte Carlo introduced by Tekentrop and Scheichel, and that would be what we call a coupled algorithm strategy. We've also looked at multi-level particle filters and multi-level ensemble Kalman filters within this type of strategy. And then approximate coupling strategy is sort of backwards compatible with the importance sampling strategy in the sense that if you can use this, method, then you can use this method, but this method is also applicable in contexts where you can't use the importance sampling strategy. So it can be thought of as a sort of trivial subcase of this. All right, so without further ado, so this is, I don't get busted out by TC this time at least. You probably might recognize this slide if you saw TC's talk last week. So these images are courtesy of him, and they're coming from his thesis, where he worked on this inverse problem of inverting measurements at a geothermal reservoir in order to infer the subsurface properties, so subsurface permeability, permittivity, and so on. And so here we're just going to assume this sort of simplest of ansatz connecting the observation with the forward model. So this is going to give rise to the likelihood, which is just going to be the difference of y and g of u. And it will be determined by this, the distribution on this observation model errors, which, as you may have guessed, will be Gaussian. So, so we have like the likelihood is going to be given by a nonlinear least squares, exponential of a nonlinear least squares term. So the data are limited, noisy, and indirect. The parameter could be a function, discretized. In this case, it is. In this talk, it's not going to be, but we have looked at that case. And so this function g now needs to be approximated. So I've highlighted this because this is the issue that we're focusing on, and that one is focusing on typically when using these multi-level Monte Carlo methods. All right, so this is sort of obvious, I guess, to everyone here. So what do we want to do? If we want to solve this inverse problem, but we want to solve it from a Bayesian perspective, then we want to find the posterior distribution, right? So ultimately, we want to compute quantities of interest given as expectations with respect to the posterior. There's a connection with classical inverse problems in as much as you are maximizing probabilities. Point of maximum probability typically corresponds to some analogous solution of a classical inverse problem. I don't see that many inverse problem people here who I recognize, so you can think of that as, say, the regression problem. Often you have an analogy with a regression problem and maximizer, maximum a posteriori estimator from the Bayesian perspective, regularized regression. All right, so here we're aiming to approximate expectations with respect to some probability distribution. I'll denote eta infinity, which needs to be approximated at some finite resolution, and we'll denote that by eta L capital. And this eta L capital can only be evaluated up to a normalizing constant, at best. Actually, I'm going to give another talk on Friday where we loosen the requirement that we can even evaluate it and only require evaluation up to a non-negative unbiased estimator. But for now, we can evaluate it up to a normalizing constant. So MLMC will be utilized with sequential Monte Carlo samplers, yielding SMC Sampler for Bayesian inference problems. And of course, I'll also do a brief summary of some additional methods. So MLMC methods reduce the cost to get an error level of epsilon, and they can be used in the case that eta L can be sampled from directly. This paper is Heinrich from 2000, and this is a paper by Mike Giles in 2008. So the methodology was first introduced. It first appeared in this Heinrich paper, and there was very little work until 2008 when Mike Giles used that methodology to estimate expectations corresponding to option pricing. And subsequent to that paper of Giles in 2008, there has been quite a bit of work in this area. And it was not, however, until 2013 plus where we started to see multi-level Monte Carlo applied to the type of Monte Carlo algorithms we've been hearing about so far in this program. In other words, in the Bayesian context. So here it's assumed that we can't sample directly from eta L. So we can't get IID samples, but we can evaluate it up to a normalizing constant, as I said, at least for this talk. This is the Huang, Schwab, Stewart multi-level Markov chain Monte Carlo from 2013. Scheichel, Teckentrup, together with Kettleson and Dodwell, have a different multi-level Markov chain Monte Carlo. This is the Beskos, Jazra Law, Tempone, Zhu paper from 2017 where we introduced the SMC samplers, and this is a whole Tempone Law 2016 multi-level ensemble Kalman filter. I'll mention now so you can keep it in the back of your mind, my talk recently grew from 50 minutes to an hour 40, so we will take a break after this set of slides. And there's going to be another talk of slightly shorter, and I'll give you the choice on that one. I'm either going to tell you about multi-level ensemble Kalman filter and particle filter. That's a coupled algorithms example. Or I can tell you about extension of the SMC samplers, which we did, which is called SMC DILI. It has to do with some MCMC method that we developed that is particularly efficient for these type of inverse problems. We call that DILI. And I don't see any DILI people here, so I'm suspecting you're going to go with the multi-level particle filters. But anyway, so you can keep that in mind. I'll come back to that at the end. That question at the end. in this, so this is a multi-level ensemble Kalman filter. So maybe I'll tell you in a bit more detail about that later. I have at least one slide about everything at the end, so of this sort of set of slides. All right, SMC samplers. I think most people here probably know about SMC samplers. It's a general method, comprises a general class of algorithms which are effective for sampling from these types of targets. This is a paper by Radford Neal in 2001, annealed importance sampling. There was a paper by Chopin in 2002. And then this is, of course, Delmoral, Duce, Jazra, 2006. And there was a paper, or an earlier paper in physics literature by Jarzynski, or two papers maybe. Okay, so multi-level Monte Carlo sampling. I'm assuming that this is probably going to be the most the most foreign for the most people here. So I'll try to go through this. I'll try to go through this carefully. It's not too difficult to understand, but anyway, yeah. So this is a prototypical context where you would apply multi-level Monte Carlo, the sort of vanilla multi-level Monte Carlo. So the expectation of some SDE, which we cannot solve exactly. So for of course a wide class of f and sigma, there is a solution of this SDE, but for only a very small subset can we actually solve the SDE exactly. So in a sense, what I mean by solve exactly is for very few pairs f and sigma, can we actually sample from xt capital? And ultimately, we want to estimate expected value of some function of the solution at the final time of xt capital. So typically, what we're going to need to do, so it's in some very few cases, we can just get IID samples of the solution at the final time, and then we would just take some n and we approximate the empirical average. But for most cases, we'll need to approximate the solution at the final time. For example, with Euler-Maruyama method, which takes this form for a resolution h. So we take some nt capital standard normals, and then this is just Euler method, and then this is how one approximates increment of this term here. All right. So, and I apologize if I'm slightly insulting anyone's intelligence, but I figured that since I'm going to talk for this week for 50 minutes times 3, 150 minutes about multi-level Monte Carlo type methods, and I'm only going to talk about the multi-level Monte Carlo bit once, I better be sure to cover it thoroughly. So for sure, this is obvious to everyone here. So single level Monte Carlo. So the reason why I have this slide is just to contextualize the multi-level Monte Carlo, not to insult your intelligence. So we want to approximate an expectation with respect to some measure. So if we write this in a general form, we want to approximate eta infinity of g, which I define to be the expectation of some g, functional g over e, with respect to this limiting infinitesimal measure eta infinity. So the typical naive approach would say, okay, we're going to, first we discretize the space. So we approximate eta infinity by eta L capital. Then we then we draw some NL capital samples, ULI, and then we compute this empirical average here, which is now, is unbiased estimate of eta L of G. And indeed, the mean square error can be split into a sum of the variance and the bias, and the bias squared. And so now, in order to drive down this bias term to an acceptable level, we're going to have to increase the resolution L capital, and then in order to drive down the variance, we're going to need to increase this NL capital. So we're going to need to take enough samples to drive down the variance term, and we're going to need to take a fine enough resolution, in other words, large enough number of degrees of freedom to get an acceptable bias over here. So if we want to achieve, for example, a cost, if we want to achieve a mean square error of size epsilon squared, then the cost is going to be the cost to obtain a size epsilon bias times times epsilon minus 2. So we're going to have to take basically epsilon minus 2 number of samples, and each sample is going to incur this highest level of cost. All right, so so the idea of the multi-level Monte Carlo is, okay, we have some limiting thing, we have some kind of convergence happening here, so is there some way that we can leverage approximations on different levels in order to improve that total cost to obtain a mean square error of size epsilon? So yes, there is. So bear with me. This is 2 slides. The description is 2 slides. So let's suppose we introduce a hierarchy of discretization levels, E to L, from 1 to L capital, and we define YL to be this increment between successive levels. With then some convention that eta minus 1 is identically 0, we can write the expectation with respect to the E to L in terms of this telescopic sum, right? Now, each one of these terms of the telescopic sum can be unbiasedly approximated by estimators of this form. In fact, any estimators of this form, provided that these pairs of samples UL minus 1I admit the appropriate marginals, right? And in particular, they can be coupled, and that's what we'd like them to be. We'd like them to be coupled in some optimal or maximal way. So as I said, okay, we're now the objective now is to obtain pairs UL minus 1I distributed according to eta bar L, which where eta bar L is some coupling which admits the appropriate marginals. And now we're going to approximate the expectation at the final level L in terms of this multi-level Monte Carlo estimator. So each one of these YL, NL is a Monte Carlo estimate of one of these increments. And these also, by the way, are independent between levels. Sometimes we put an additional L there to indicate that that's the level L minus 1 sample from the level L versus the level L minus 1 sample from the level L minus 1. Or sometimes people will write sometimes 1 and 2 or coarse and fine for each L. So then the mean square error is given by the sum of, again, it's given by the sum of the variance and the bias, but now given also this assumption of independence between levels, the variance is going to split into the sum of the variances at the individual levels. So now instead of having 1 and n inverse, we have the sum of the variance of the level L estimator divided by the number of samples at level L, and the bias is just the same as it was before, right? So in fact, these assuming that the variances, these VLs decay, then we can get away with taking fewer samples at the higher levels. So VL decreases, then we can let NL decrease and thereby reduce the total cost. So that's sort of the heuristic idea, and you can make that rigorous with the following. So you say, okay, we're going to fix the bias by choosing L, and we minimize the cost as a function of the numbers of samples for a fixed variance, and then we find out that we should take NL to be proportional to square root of VL divided by CL. And so the CL is the cost of obtaining a pair of samples at level L. So CL's increasing, but it's appearing in the denominator, and then the VLs we're assuming are decreasing. And so indeed the NLs can decrease quite strongly. All right, so before I make that, say a rigorous statement about MLMC, let me just show you a quick description of what is this, what do I mean by pairwise coupling, or how would you do that? So for example, for the simplest case of this vanilla MLMC for estimating expectation with respect to a SDE, it's quite straightforward to do this. So the pairwise coupling of trajectories in SDE can be accomplished like this. So this is just two levels, a coarse level 0 and a fine level 1. So we draw some N1 standard normals and we run Euler-Maruyama. And that's giving us this green trajectory here. Well, okay, so left side is the Wiener process driving the SDE, where W1 now is given by the sum of increments times square root of h. And then over on the right are the trajectory of the SDE. I think that this is a case where it's just an OU process, so these are just linear. So this is linear and this is constant. And so then you couple the SDE by summing every second increment from the fine level, summing every second increment from the fine simulation, and that gives you then a coarse simulation which agrees where the Wiener process, the coarse Wiener process agrees at every second discretization point. And so in particular, realizations stay close, the variance is small, and ultimately the variance of realizations of the SDE also are going to stay close. All right, so now what does that mean in terms of complexity? So this is, here we look at the cost of multi-level versus single level. So we'll introduce some assumptions about rates. For simplicity, let's let HL be 2 to the minus L and assume that we have some alpha and beta bigger than zeta so that we have a weak error of rate HL to the alpha. That's the absolute of the difference in expectations between the discretized and the limiting process, and a strong error rate of convergence beta, that's the expected value of the square of the difference. So this weak error is going to dictate the bias, and then the strong error is going to dictate the variance. And furthermore, we assume that the computational cost for one realization of UL minus 1 scales like HL to the minus zeta. So this is, of course, reasonable because your number of degrees of freedom are going to be inversely proportional to the step size. In fact, as it's been pointed out, zeta for SDE is always 1. So, but it's not 1. You know, there are contexts where it's not 1. PDE, for example. Okay, so both cases require that HL to the alpha is size epsilon, and then that means that L is going to be proportional to absolute of log epsilon. So now, okay, so now we can now represent the cost at the final level also in terms of epsilon. So that's going to be like epsilon minus zeta over alpha. And then, of course, for a fixed variance of epsilon squared, we're going to need NL to be proportional to epsilon to the minus 2. So this is going to give a single level cost of epsilon minus zeta over alpha minus 2. The multi-level cost, on the other hand, so for multi-level, we're going to choose these NLs for little l is 1 to big L to be of this form, and that will ensure that we have a variance of epsilon squared, and then we'll be able to represent the total cost in this way, so like epsilon minus 2 times KL squared, where KL is this sum of these of terms like this, so that's related to the way that NL looks here. So this is why I chose this beta bigger than zeta, because then you have this term as order 1. Of course, it's going to be bigger than 1, but it's not going to be proportional to epsilon, right? So there's typically with these multi-level Monte Carlo methods, you'll get some larger constant, but always a better rate. So in particular, the rate now is going to correspond to the rate of cost for error level epsilon is the same as the rate for simulating a scalar random variable. So for example, for Milstein's solution of SDE, we have beta is 2 and alpha and zeta are 1, and the single level cost is epsilon minus 3, while the multi-level cost is epsilon minus 2. So epsilon minus 2 is your sort of your standard Monte Carlo rate if you swap the role of cost and error of n to the minus 1/2. But for these problems where you have these two sources of approximation error, you can often get quite a bit worse than that, actually. So like, you know, n minus 1/3 or n minus even 1/5 for some kind of PDE type problems. Okay, so to make the example concrete, so let's suppose that let's consider this sort of simplest prototype PDE example, or ODE in the case that d is equal to 1. So we have, so this u bar is a diffusion coefficient, which is given by some mean term plus some sort of what you can think of as something like a truncated KL expansion. So we're assuming now that that u hat is living in a k-dimensional, finite k-dimensional subspace of a function space. These sigma k are some coefficients. Phi k you can think of as, for example, sine or cosine functions, and the uk are uniform random variables between -1 and 1. So the state space in this case is this k-dimensional hypercube. That's the prior, and assuming that we have some appropriate conditions on these u bar and phi k and sigma k, in particular, that we ensure that almost surely with respect to the prior, this u hat of x is bounded away from 0. Then we have some uniform estimates on the solution of this PDE, and so that's so everything sort of works out nicely for this example. Okay, so then the inverse problem is the following. So we're going to assume that we have some g, some functionals g at m capital number of these things, and we evaluate those at p, and then the observations are going to take this form. So they'll just be the evaluation of the solution at these functionals and then corrupted with some Gaussian, additive Gaussian noise. So then we can write the unnormalized density, and it's just this negative, this exponential of a quadratic in G, sorry, which is nonlinear, which is a nonlinear function of U, of course. So it's not just Gaussian with a uniform prior in the end. And then the thing that we get, the troublemaker for the Bayesian context is this guy here as the normalizing constant, which we don't know. All right. So SMC samplers. I just have this one slide, and I think that this is good because everybody here should pretty much know what I'm talking about. So the distributions E to L. So here we're going to let the distributions E to L be dictated by an accuracy parameter, the finite element mesh diameter. So the method's general, but I'm putting it in the context of the example I introduced in the previous slide. So we approximate. Lost my big pointer. The thing, I like this pointer because you can see it always from the back of the room. It's got this nice big thing, but then it runs out of batteries quickly. So, all right, I think maybe it's still going for now. All right, so we interlace sequential importance resampling along the hierarchy with mutation by MCMC kernels. So we'll initialize by some n samples distributed according to E to 0, and then we resample according to the weights, which are the normalized, which are these normalized selection functions GL, where each GL is GLI is the ratio of successive unnormalized targets evaluated at some UI. Then, and then we're going to run each sample through a MCMC kernel that keeps the current target invariant. right? So this is the importance sampling step is going to guarantee that we is going to guarantee that our particles are distributed according to the appropriate target, and then this jittering mutation step is going to diversify the population at each step so that we don't end up getting some kind of degeneracy, since we're sort of making up this SMC method where one ordinarily wouldn't wouldn't exist. All right, so now we're going to, assuming that we save those samples all the way along these iterations, then in fact we have estimators for each L of expected value of e to L for some function g, just given in terms of the empirical average over those n samples. So ordinarily what you would do is you throw away all the samples up to level L capital, and then you estimate, and then you just use those capital N samples at level L capital to estimate the final target. So maybe you can then see where we're going with this. So in fact, coming back to that multi-level Monte Carlo estimator, we like to represent the expectation with respect to level L in terms of this telescopic sum here. And now we're going to approximate this telescopic sum. These are each expectations with respect to one of the e to L's using the SMC sample hierarchy. So that's it. The key thing in order to get payoff for doing that is that we're going to subsample. So for each level, we'll subsample according to some carefully chosen schedule of sample numbers n0, n1, and so on. So we're going to have to get some estimates over here, and then that's going to tell us how we should choose these n sub L's. And then we'll run SMC samplers, but we're going, at each step, we're going to take a subset of the samples where we've chosen that subset of samples in an appropriate way. Not the specific subset, but the number of samples in the subset will be chosen in a specific way. Okay, so this is now a consistent estimator of e to L capital. It's given by this sum here. So each of these terms is estimating one of the terms we wrote on the previous slide. Okay, so one thing that people sometimes find bothersome is that these are not unbiased estimates, and so you don't exactly telescope. But in fact, you still have error estimates, and you just have estimates like you can just use this inequality here. So if these things are both small enough, then this is small, regardless of whether this is an unbiased estimate of this. And if you want to write it in terms of bias and variance, you just get more terms, because you always have to use this guy here. And so the same L+1 estimates are not independent, so we require a more complex error analysis in order to characterize this variance-like term. So for the particle filtering people in the audience, this in particular requires the same type of estimates that you require for time homogeneous estimates, error estimates for particle filter. We need decay of correlations. So otherwise we accumulate error on the different from the different levels. Okay, so we need the weights to be well behaved. So this is sort of strong. This is sort of a strong assumption here, but sufficient. So we'll have some uniform bounds both above and below for G, the GLs of U over L and over U. And so we have some very strong mixing condition on the MCMC kernels. Typically, we expect that these are going to be a bit stronger than one will need in practice, but okay, it's sufficient. And furthermore, we're going to need an estimate of this type. So again, the ZLs are the normalizing constant with respect to level L, and then these this GL is kappa L divided by kappa L minus 1, where kappa L's are the density, unnormalized density. Okay, and so these, so yeah, this is also a fairly strong requirement, but sufficient. And in fact, we can have that for that well-behaved PDE that I introduced earlier. Right, all right, so if we have that, those three assumptions, and for any G we have this type of bound on the variance, and of course the bias-like term just comes from standard estimates for discretized solutions of PDE, and this variance can now be bounded in this form, and in fact we find that in the case that beta is bigger than zeta, these are the dominant terms in the sum. So these are the terms that arise because of this, because of the correlation between levels. Since we're stepping through this SMC hierarchy and using samples from the same SMC for the different levels. All right, but so this is good. So that's a great success. Then we can choose L and NL in the NLs from 0 to L, so that we can get a mean square epsilon squared for computational cost of epsilon minus 2. So that's the optimal case. All right, so this is just illustrating that for that PD example we looked at. I can't remember if the dimension is 1 or 2, but this capital K is about 50. So this is a 50-dimensional diffusion coefficient, and we're estimating that using this multi-level sequential Monte Carlo versus sequential Monte Carlo versus a standard sequential Monte Carlo method where we don't subsample and we don't use a telescopic identity. And you can see, so this is mean square error decreasing from right to left, and cost is increasing from bottom to top. So when we ran out of power for the SMC, we had this mean square error 2 to the minus 20, but we made it all the way down to 2 to the minus 26 using ML, using the multi-level thing. So this stuff is really paying off when you want very accurate solutions to posterior expectations, which involve some discretized model appearing inside the target. All right, so now I'll tell you briefly about some other multi-level Monte Carlo algorithms for inference. So what I was describing, what I just described is what we're calling an importance sampling strategy. So that's where we rewrote each term, each increment in terms of importance sampling with respect to one of the levels in the increment. And as I mentioned, that was the same strategy that was used by Stewart, Schwab, Huang for their multi-level Markov chain Monte Carlo. So we did a bit more work using this strategy, and then we started to explore some other strategies for coupling these successive targets suitably well, so that we're actually able to apply these kind of Markov chain Monte Carlo, sequential Monte Carlo types of algorithms. Yeah? What's up?
So you have access to the unnormalized density for the L with L minus 1 level, but what do you do about the normalizing constants, that ratio? What do you do with that in the algorithm?
For the ML-SMC sampler,
yeah.
we just have this thing here. So this guy's the actually estimate of the ratio of normalizing constants. It's not unbiased, but it's consistent.
What's the big G?
Big G is the ratio of the unnormalized densities. So it would be like GL minus 1 is kappa L divided by kappa L minus 1. So this thing here is approximating this thing here consistently. Not unbiased, but consistent.
Okay, so it's consistent.
Yeah.
And so when
No,
You
it's,
have the variance of the bias. Let's see. So you have the bias from the highest level, but you're also assuming that.
yeah, I mean, it's not really bias, but it's bias-like. So it's not, this isn't a variance bias decomposition. This is just a bound. We just split basically between, just add and subtract this guy, and then you have that bound. You just have these twos there. So if it was unbiased, this would be equal and there would be no twos, right? But actually it's okay. The analysis works out, even though it's not unbiased. Okay. Maybe we continue in the break. We'll take a short break of 5 minutes or so, I think, in between. Yep. Well, we actually can't use that estimator, but in fact we can construct, and we did construct some unbiased estimators for the normalizing constants in this paper with Pierre in 2016. But we picked up an additional, this additional logarithmic factor in the cost. But in fact, we can do that in one of two different ways, one more complicated and one slightly less complicated. But we figured out that the less complicated one works after we've developed the more complicated one. So. And here it's quite natural to do the RMLMC, the randomized multi-level Monte Carlo estimators of Rhee and Glynn type. And so these are those two. This is just a plot just like the one that I showed on the previous slide, except actually we even have a better constant here for some reason, where we use this is the normalizing constant estimator, not using the multi-level tricks, and then these are each of the two estimators that we developed using multi-level. So that was again important sampling. We use quite a analogous strategy there. So this is one of your options actually when we choose your own second half later. ML-SMC samplers with DILI mutations. So we look at the case where, okay, now it's actually what you sort of can comfortably call Bayesian inverse problems. So we're trying to actually sample from a measure over a function space. So in principle, we have a target where the unknown is a function. And then we have also another layer of approximation coming in discretization of the PDE mapping the unknown to the data. So we represent that like this. So that could be level L could be, say, twice as many or 2 to the d as many discretization points in your approximation of the SDE or the SPDE. Or it could be, for example, 2 to the L times D coefficients in a spectral expansion of Fourier basis or something like that. We introduced something. So in this paper, we introduced this type of MCMC methods, which are based on a formerly introduced likelihood-informed space. And we extend that notion for the SMC samplers context by introducing this covariance-based likelihood-informed space. So this likelihood-informed space that went into the original DILI MCMC involves derivatives. We used derivatives to find a space of concentration of measure and thereby accelerate the MCMC sampling. So we introduce a new kind of likelihood-informed space, and which leverages the fact that we have ensemble of samples approximately distributed according to the given intermediate target with SMC samplers. So we use empirical averages, and we use those in particular in connection with these Dilley type proposals so that we get something that's nice and dimension independent and efficient. And we get a substantial reduction in cost, but when you look at it on these log error versus, well, one of these is cost, so this is cost. That's wrong. Sorry about that. When you look at them on these logarithmic error versus cost plots, it doesn't look that impressive because it's just this constant here. But the constant's pretty significant. I mean, it's 10 or 20. Sorry. So this again is the normal SMC. This line here, and then this is MLSMC using a standard type MCMC proposal that scales well with respect to dimension, so-called dimension independent or function space MCMC. This one, and then the Dilley MCMC is this red one. So we pick up this. So we have the same rate because we're not going to get any better rate when we're doing the same algorithm, but we do pick up this constant. And this work is ongoing as well, and it's not unrelated to this dimension independent version of RTO that TC was talking about last week, and I think he's going to talk about some other work in that area later this week. Hey, TC, I didn't see you here before, so I'll do a vote if we want to talk about that or the other thing, or this stuff. Okay, so TC will talk more on Wednesday. Good. All right, so for coupled algorithms now, that was all important sampling. So coupled algorithms, we looked at multi-level particle filter, and I apologize in advance to other authors who worked in this area because I'm sort of surveying a lot of work in multi-level Monte Carlo methods for inference type problems, but I'm only our work actually, not other people's work. Of course, I did mention that the Scheichel MLMC falls into this category. And in fact, Sebastian Reich, together with Colin Cotter, looked at multi-level ensemble transform particle filter, which also falls into this coupled algorithm type of strategy. So filtering, everybody here knows, okay, that involves a sequence of Bayesian inversions separated by propagation in time. So we'll assume that that's given by propagation through a SDE. We can't solve the SDE exactly. So then, so what do? So we now will have an ensemble over levels of pairs of particle filters at each time. And then we can use coupled, right, so we'll use coupled traditional SMC algorithms for each level. Each level will have a pair of coupled particle filters. So the question then is, well, how do we couple these particle filters? Well, mutation, it's quite obvious. I showed already early on. You use the same method that Giles used to estimate the expectation of options. And so it's given by a coupled propagation of a pair of initial conditions through an SDE at two successive mesh refinements. And then the selection. So the selection then, it's the resampling that causes the trouble, right? So you have this coupled propagation, so you have your trajectories are coupled. Then you reweight, but we all know that you can't just keep running a particle filter without ever resampling. And so it's at the resampling time where we have to figure out how to do the resampling, how to keep the particles coupled when we do resampling. And so we use a maximal coupling. So we sample a multinomial. So we sample from a maximal coupling of the successive levels, which preserves the marginals and maximizes the probability that any two indices will be the same before resampling to after resampling. Okay, so that works, but actually we believe that or in fact the analysis reveals that it's at the maximal coupling stage that, okay, we do preserve coupling, but we we lose the rate a little bit. So if we had beta rate of convergence of the forward, if we have beta rate of convergence of the approximation of the SDE, in other words, for this mutation, then we end up with a beta over 2 rate for the filter, for the particle filter. So we lose a little bit of the rate there. And we're looking at the moment at a new version in which we are able, at least in certain contexts, to preserve that rate using an L2 optimal coupling instead, which may be arguably more natural thing to. All right, so these are simulations. So these are this is Euler-Maruyama method with for these two cases have constant diffusion, and then with Euler-Maruyama you get effectively a rate of beta is 2, and these two have non-constant diffusion, and so you get a rate of beta is equal to 1. So actually, since we have this reduction in beta being the strong rate of convergence, the rate of decay of the variance, we'll get in this, will be either in the borderline case of beta equals theta, or beta equals 1, or the case of beta less than 1 for these two here. So again, I'll just remind you that that's going to be, when we break, is for those of you who are brave enough to come back for the next half hour after we break, I'll either talk another half hour about this stuff, or about these two things, so that multi-level particle filter and then multi-level ensemble common filter for SDE. We recently extended this to SPDE as well. So ENKF uses a sample covariance from an ensemble of particles to approximate a linear Gaussian Bayesian update given by an affine transformation of the particles. Okay, we've seen this method a few times already last week, the ENKF. So we do multi-level ENKF. So we do a multi-level approximation of the covariance, and we're able to improve the cost. In fact, and I think that this may just be an artifact of the analysis, we have this sort of geometrically growing logarithmic penalty, which is geometrically growing in n, and we can't seem to get rid of that. But we use an inductive approach, and it's sort of natural to expect if you have no kind of stability estimates to have something like that. So we'd like to get rid of that. That's ongoing work. Yet numerically we see, in fact, even uniformly in n, so even in the sense that the constant is uniform in n, the rate that we'd like to get. So there's a bit more to be done there. And recently we extended this to the context of SPDE. So we have the same n dependence, and yet the method should be much more broadly applicable. For example, to these type of contexts where people are typically applying ensemble common filter, weather prediction, and so on. Okay, so on then to approximate coupling. So this was our first example of the approximate coupling strategy, and this I'm going to not do justice summarizing in 2 slides, but I am going to give a talk on that on Friday. So if you're still around, I'll go into the full detail on this method on Friday. So here we aim to estimate, for example, expectation of functions of the parameter of an SDE given some finite set of partial observations. So here the x theta t is the solution of a SDE given this value of the parameter theta. Okay, and it's parameterized by theta. So this particle MCMC, or in fact particle marginal metropolis Hastings in particular, not to be confused with the particle Gibbs, which has been talked about already a bit here this week. Particle marginal metropolis Hastings goes like this. We propose a theta theta prime, simulate a particle filter targeting the posterior given that value of theta prime. Then we compute the non-negative and unbiased estimator of the marginal likelihood, and we accept or reject using this approximation, this unbiased estimator of the marginal likelihood. I've brushed something under the rug here, which is that in order to get samples of the path, we have to make sure to trace the ancestral lineage. So we're going to need, even if we want to estimate expectations with respect to phi, we're going to need samples of the path at successive levels. Okay, so how do we do that? How do we do MLMC in this type of context? Well, we have these approximations of the SDE on successive levels. We don't know how to couple the posterior at two levels, right? But what we actually can do is we can construct an approximate coupling. So we define this approximate coupling by using, for one thing, the usual coupled forward kernel. So the same thing I mentioned for the particle filter, the same thing I described in a very early slide, in the same way basically that Giles couples the pairs of solution of SD on successive levels. But then we have this selection or resampling that we need to deal with again. So with an approximate coupling strategy, we say, okay, let's define this new coupled selection function. Here we define that to be maximum of the selection function evaluated at the two, at the coarse and fine. You can also use, we are using in a recent instance of this where we've renamed that, this procedure delta particle filter. We use here 1/2 average of the two guys. This is with Matti and Jordan, and I think Jordan will actually talk about that stuff at some point. So now we have these HL and HL-1. We define these weights, which are the importance weights to estimate the coarse and fine respectively with respect to the coupled. So we've got this coupled particle filter. It doesn't have the right marginals, so we do importance sampling to re-weight. And the reason for this choice, and which actually the choice of the average also satisfies, is that the weights are bounded by 1. And so we've got, in particular, the estimates are well behaved. So they'll have well behaved weights here. So we estimate the increment like this. And now the optimal results hold with the same rate as the forward problem. So now, whereas before we were decreasing beta to beta by 2, for this case we preserve the same strong rate of convergence beta for estimates of this type. Of course, this is we need weights with respect to the whole path, so it's not really online. But that was quite nice. And in fact, this approximate coupling strategy can be used in many other contexts as well. So the first example of that we looked at was multi-index Markov chain Monte Carlo. So if you have a spatio-temporal approximation dimension d greater than 1, then multi-index Monte Carlo is preferable to multi-level Monte Carlo. So this paper is Haji Ali Nobile Tampone, coming from Abdul Haji Ali's thesis at KAUST in 2015. And so they suggested, well, okay, maybe we can do multi-level. We're discretizing different directions, right? Maybe we can do multi-level independently in different directions. And okay, it turns out under suitable assumptions you can do that, and you can substantially accelerate the convergence. So here we define, find this difference operator delta I like this. So you take a difference, this alpha is a multi-index, and you take this difference in the ith index. like this, and then you define this this del operator to be the product of the dels over the d dimensions that you're approximating, and then you can now write the infinite resolution expectation in terms of the sum over all the multi-indices of these del type operators. All right, and then in fact, so you can approximate that. In these guys, you assume that these guys are decaying somehow. So you can approximate that by the sum over all the multi-indices in some set. So the naive thing to do, which would come straight from the multi-level, would be to take a tensor product set. You sort of divide up to some number of levels in each direction independently, and then you have some cube. But in fact, you can get your hands on simplices, which give you much better rate of convergence of estimates of this type. And in fact, right, in terms of cost complexity. Okay, and then so in fact also now in the inference context, we can just apply approximate coupling to each of the 2 to the d probability measures arising in each summand. So it's sort of something quite natural that we can do there. We take the approximate, so we do that. So we looked at that. This is just a cartoon of what's going on with multi-index. So you do like a difference here, and then you do a difference of this difference with this level as well. So you do a difference and then a difference of a difference, and you end up with four measures for each summand for that multi-index stuff. Okay, so in summary, multi-level sequential Monte Carlo sampler can perform as well as MLMC. We had beta bigger than zeta. If beta is less than or equal to zeta, you get a somewhat higher cost. That same thing happens with multi-level Monte Carlo. If zeta is bigger than 2 alpha, then the best you can do is a single simulation at the finest level. And that happens a lot with PDE, actually, or SPDE. So the newer, I guess I should say, because that's now published by now, importance sampling example is this multi-level sequential Monte Carlo with Dili mutations. Coupled algorithms I talked about were multi-level particle filter, where we had this reduction in error rate, and then multi-level ensemble column filter, where we had this independent logarithmic penalty. In fact, I guess I would venture to say that all of the coupled algorithm examples are somewhat suboptimal in some way. It seems to be much more difficult to couple algorithms versus like approximate coupling or importance sampling, wouldn't you say? So we do have some new work, which I'm sorry that I didn't put into these slides. I had sort of a small amount of time allocated, and I was going to soup these up, but instead I sort of revised some other old slides to do this part 2. So this is very nice recent work with AJ and with Linda Shu, who's here, a postdoc here with AJ. Multi-level Markov chain Monte Carlo using coupled algorithms, and yet different from the Scheickel coupled algorithms, multi-level Markov chain Monte Carlo. So there are now, in terms of multi-level Markov chain Monte Carlo algorithms, this is the 4th different one. And that one is quite nice, but it's not very good. It has troubles with rejections. So you want rejection-free MCMC. So we had good results with Gibbs sampler for a certain target, but we didn't get good. We didn't find good results with Metropolis Hastings, unfortunately, with that one, which you'd kind of like. So on Friday, I'm going to talk about that approximate coupling with the multi-level particle Markov chain Monte Carlo for SD parameter estimation, which preserves the strong error rate beta. So new approximate couplings, actually this I had a slide on that multi-index Markov chain Monte Carlo. We also, with Linda, looked at multi-index SMC squared. So that's sort of you do the SMC squared on this using this MIMCMC type method in between for the mutations in the MISMC squared. And so if you're a student or postdoc with similar interests, or if you know some of them, then please let them know that positions are available at Manchester. These are the references. This is the multi-level SMC samplers, multi-level SMC samplers for normalizing constants, multi-level particle filters. This is an application paper. We looked at an elliptic non-local equation with both forward and inverse MLMC, multi-level ensemble common filter. This is the original Giles paper, the Heinrich paper which preceded it. This is multi-index Monte Carlo. Of course, SMC samplers, and the earlier Chopin paper, and it looks like I lost the Radford-Neal paper of 2001. Pierre's book. This is the Dilley MCMC paper with TC and Yusuf. This is the original MLMC of Schwab and Stewart. The earlier MLMCMC by Scheichel, Tekentrup, and there was an additional author in the final version, which is called Dodwell. Here we extended multi-level SMC to spatiotemporal. This is what I'll talk about on Friday, this MLMC for static Bayesian parameter estimation, the first example of the approximate coupling. The multi-index Markov chain Monte Carlo. Here we tried to summarize most of the stuff that I talked about here, actually. This is a review paper, it's only on the archive at the moment, but we've tried, actually, I think we've done quite a good job of condensing that all down into a concise single paper with Karina Susio. This is this MLSMC samplers with Dilley mutations paper, which is now also published. And these are the two papers with recent papers with Linda, which are both available on the archive but not published. Thank you. Okay, welcome back. I hope you managed to have a tea or coffee or something like that, and everybody's refreshed. All right. Yeah. So I'll talk about two different methods for filtering or / data assimilation: the particle filter and the ensemble Kalman filter. So the particle filter is joint work with AJ, with Kengo, and Yan. And the ensemble Kalman filter then is joint work with Hoken and Raoul. Hoken Hole and Raoul Tampone. Okay, so I'll introduce the filtering problem, then particle filter. And so these, I guess I can go quite quickly. And then, since they've been introduced already several times before, multi-level particle filter, then ensemble Kalman filter. Maybe I present it in a slightly different way, so I'll go through that, and then I'll introduce this multi-level ensemble Kalman filter. Summarize. Okay, so now we're going to have a sequence independent of the levels. So we're going to have our multi-levels are going to be so we're going to be stepping through a sequence of targets, and the levels are going to at each time point we are going to have multiple levels corresponding to different discretization levels. So we want to approximately sample from a sequence of probability distributions, eta infinity m, which need to be approximated by some eta lm for m for this sequence of times m, which could in principle be indefinite. We're not going to bother too much with that question at the moment, but both of these algorithms can in principle be online algorithms. Multilevel Monte Carlo framework will extend that to the multilevel particle filter and ensemble Kalman filters. So again, you know, multilevel Monte Carlo allows us to obtain an error, approximation error at the level of epsilon efficiently, and it can be used, the vanilla version of Giles 2008 can be used in the case that we can sample directly from any given discretization level, and of course couple two discretization levels. I guess I should have written that. Here it's assumed that we cannot sample directly from the levels, and we cannot couple successive levels either. So particle filters are SMC algorithms that provide consistent approximations. Of course, I should have cited the Gordon paper of 1993, but this is Pierre's book for 2004. Ensemble Kalman filters are SMC algorithms which provide approximations of such distributions as well. This is Evanson 2006. And these methods are typically have been adopted in very high dimensional problems where people have sort of abandoned any idea of any hope of trying to get something consistent. So they're not consistent, but they're convergent. So they converge to something else. It's not the posterior distribution, and we don't really understand that thing that they converge to that well. But there are reasons why it's of interest. Okay, so the filtering problems like this, so we're going to have xn plus 1 is distributed is a draw given xn from some kernel, Markov kernel Q. Yn given xn has some density that's known for given values of yn and xn that need not be normalized. And so we're aiming to approximate the posterior expectation given historical observations up to time n of some function of the state at time n, where yk is a realization of capital Yk and phi is some it's just some functional. So the joint probability density of the state and observations given the initial data takes this form. And we'll furthermore, so in the context here today, so we're going to further assume this additional difficulty, as we had in the previous talk, that we cannot sample this xn plus 1 even if we know xn. We can only sample an approximation. So we'll have some approximate Markov processes, xl n plus 1, which is dictated by this approximate Markov kernel ql, and these L will correspond to resolutions, approximation levels of the limiting SDE, and so in this notation then Q infinity is defined to be the Q. So that's what we'd like to solve. We can solve that by replacing this guy here for any L or for many L's, and we'll argue that actually it's a better idea to do that for many L's in a pairwise coupled way. Okay, so particle filter then, so suppose we discretize at level L capital with this Markov kernel QL, then the kernel associated, so this is a kernel associated to level L with initial condition X. Will be the Euler-Maruyama discretization of an SDE with some discretization parameter, some time step size HL. We're going to generate this for each, well, okay, so this is just a single level particle filter. So we're going to generate this empirical distribution using particle filter. So we draw samples from the initial target, and then at each step we iterate, drawing each sample taking one step through the Markov kernel for each sample, and then drawing index according to the multinomial corresponding to the normalized selections, and then we update the particles according to the resampled particles. So I'm assuming that we resample at every time step. Okay, you can do much more efficient things here, but you can do all of those more efficient things also within the particle filter, in the sense that, okay, you may want to keep track of the effective sample size and you don't want to resample at every step. You might want to do some other kind of more sophisticated resampling, stratified residual resampling, and so on. But this is just your sort of simplest version of particle filter. Okay, so then what about the multi-level particle filter? So it's easy to simulate a single level particle filter. In fact, again, and I sort of mentioned this just in words in a bullet on the previous talk, it's also easy to construct a coupled kernel which has as its marginals, for example, a coupled kernel ML, which takes initial condition X and Y and has as its marginals QL of X and QL minus 1 of Y. And this is, again, this thing that I described even with the pictures before of the coupling of the two SDEs, right, at one level and the other level. So that we know how to do. And then what we want to do is we want to generate this multi-level, this level L multi-level approximation for each time point M, approximation of the level L time N filter. And so then the multi-level empirical measure is given by the sum over levels of empirical estimates of increments. And so now I've, for your convenience, used one L here for level L and then a 1 and a 2 for the fine and the coarse. Before I was using an L and L minus 1, but there was a bit of redundancy when you go from one level to the next with that method. But so here this is fine at level L, coarse at level L. Okay, so then away we go. So at the initial time, we just set the time 0 particles to be equal. Then we can evolve them through these kernels. For each level L, we evolve our coarse fine pair, updated pair at time m minus 1 to a coarse fine pair at time n. And then we're going to perform a coupled resampling procedure, which I didn't put on this slide because it doesn't fit very well. So I'll go through that independently on the next slide. So we're going to now draw indices in such a way that our resampled particles somehow preserve as best as we can the coupling between the particles before the resampling, right? So if the initial conditions are the same, they're sort of, you can't get any more coupled than that. You step through this Markov kernel, which we construct with coupled Wiener processes. So these guys are quite coupled still, but now we're going to want the resample. And so the resampling, if we just did independent resampling, then we would completely botch up the coupling. And so we're going to do that in a sensible way. Okay, and then we update the particles. All right, so how does this coupled resampling work? So we'll use, for those of you familiar with couplings and with maximal couplings, we're going to do a maximal coupling of the multinomials associated to the coarse level and fine level. So so given a multi-level ensemble at time m, for each level we define these the fine weights and the coarse weights, right? So this gives us then two multinomials. We want our fine samples to be resampled according to this multinomial and our coarse samples to be resampled according to that multinomial, and we'd like for them to be coupled. So the maximal coupling works like this. We define with some probability alpha LM defined as the sum of the minimum the minimum between the fine and coarse weights, we'll draw the fine index according to this multinomial, which is the min between the fine and the coarse. And then we let the coarse, and then we define the coarse index to be exactly the fine index. Okay, so that's great. And if we were able to do that, if this probability were 1, well, that would be the case where these guys are always equal. And then we would be exactly as coupled as we were before we did the resampling. But unfortunately, well, that's not going to be the case in general. And this alpha, while being close to 1, is not going to be 1. And so in order to correct so that the coarse has the correct, well, in fact, in order to correct so that both coarse and fine have the correct marginals, we're going to have to now correct with a with probability 1 minus alpha LM, and in that correction we're going to have independent samples. So you saw this an example of a maximal coupling in Jeremy's talk if you were here last week on Monday. So this is what it looks like for multinomial. So we'll draw the fine sample according to this correction, according to these correction probabilities, and then the coarse according to these. All right, so if we do that, then we do preserve coupling, but in fact, this probability alpha LM is slightly larger than we would have wanted. So assuming that we have a one-step strong error convergence order beta, weak order alpha and cos theta. So for example, for Euler-Murayama, alpha is beta, theta is 1. Then we have this following theorem. So under suitable regularity conditions on ML and G, for any suitably regular test function, we have this type of convergence. And of course, then there's an additional term, which is a difference between this guy and the infinite resolution thing. And in fact, okay, so if beta divided by 2 is bigger than zeta, and then we can choose L and the n L's so that we get a mean square error epsilon squared for computational cost epsilon minus 2. But note that this is different than for the forward problem. So if we have beta is, even if we have beta is 2, like Milstein method, typically zeta would be 1, and we're not going to be in this sort of optimal or / canonical regime. So we're going to be stuck with this. We have a slightly worse. We're in a slightly worse situation there. So this coupled resampling effectively reduces the rate. So for the particle filter, the term contributing to the error on the right-hand side for the for the multi-level particle filter is half of what you would have if you were just estimating the expectation of the SDE at the final time. Okay, and so we checked that numerically, and it checks out. It seems to be sharp. So take this example SDE. So we have some drift A of x and diffusion B of x. Yes.
The bit about the rate being reduced.
Yeah.
Give me some intuition, maybe why? Can you recall?
What?
Okay, if you don't.
Yeah, well, just because of it arises from this coupled coupled resampling. I don't know. Do you have a better answer than that? Yeah. So it's well, I can say it's optimal, but it's maximal, but it's not optimal. So I guess you could. In fact, I think maximal coupling, maybe this is associated to like a zero Thorder or Wasserstein, but actually, since you're trying to control L2 error, it's maybe natural to use the 2 Wasserstein. And so, in fact, there's some ongoing work that we're looking at where we've looked also at numerical results where in certain cases you can get the full rate to carry over through coupled resampling using Wasserstein 2 optimal coupling. So somehow the maximal coupling, it eats up half of your rate. And yeah, probably AJ can tell you more. All right, so, okay, and so then we have partial observations. And we take Euler-Maruyama discretization with step size 2 to the minus L at level L. So therefore, for constant diffusion, we get a beta of 2, and for non-constant diffusion, we get beta 1, or effective rates of actually 1 and 1/2. And we look at OU. So I showed already the results, actually, but these are the actual SDEs. So we look at OU process, geometric Brownian motion, a Langevin diffusion, where this pi is a student T distribution with some, I think, 5 degrees of freedom or something of that sort. And then this is just some other arbitrary SDE. And these are the observation likelihood functions, and then these are the quantities of interest that we estimate at the end. This is that 1 minus alpha, that 1 minus PL of n, which is where we got this, where we see this reduction of rate. Right, and so let's see. So these two have non-constant diffusion, and these two have constant diffusion. And you can see in fact, we get half the rate over here versus over here. And in fact, we have over here we have a rate of beta is 1 versus 2, which we would like to have. So. Sorry, let me see. Right, so this is, then these are the costs, the corresponding costs. So geometric Brownian motion, nonlinear diffusion, Langevin, and OU. Actually, these are coming from a later draft of the paper, I guess, where these figures are much nicer and more legible than the figures I showed you in the previous. And this has been corrected, so it's cost versus error here. So actually, for these cases with non-constant diffusion, even down here all the way down to 2 to the minus 28, the difference is not enormous. Quite a bit better here. And if we can get that rate half robustly, then it will be much better. All right, so okay, so ENKF now. Now I'm going to assume that the observation, that the likelihood is this G function is looking like this. So I'm going to make an assumption that we have additive Gaussian observations of linear function of the solution at the given time. And if I change from x to, yeah, maybe I changed from x to u, I apologize about that. So the state now is u. So the ENKF looks like this. This is the, by the way, stochastic ENKF, as opposed to the square root or deterministic type ENKF. Okay, so we take a sample, a step through the Markov kernel. We compute the mean, we compute the covariance, and then if we want this as sort of intermediate step, we compute the gain. I mean, ultimately, really, the thing is the covariance, but we can tidy this up a little bit by introducing this additional equation here for this so-called gain. Then we have this is the updated equation here. And these psi n j plus 1s are now distributed according to the distribution of the additive noise on the observations. So this is a noisy observation. You add another realization for each particle. So this n now is the particle index, j is the time index. So for each particle, you add, you construct this pseudo observation, which has an additional realization of the noise on there. And the reason why that you do that is because then if you were in the linear and Gaussian case where ensemble Kalman filter is, where the limiting thing is the Kalman filter, then this will converge to the limiting Kalman filter. It won't if you don't include that thing there. So that's the best explanation for that. Okay, so this thing does converge, and it does converge to this process here, which in the linear Gaussian case is the Kalman filter, or is equal to the Kalman filter in distribution. So we have we've used this bar here. So U bar Lj plus 1 is distributed according to one step through this Markov kernel at level L. Then you compute the covariance of the population, and you compute the update like this. So this is, I'm just saying again that in LP, the ensemble Kalman filter converges weakly to this mean field limit, and the rate is n to the minus 1/2. All right, so the multi-level ensemble Kalman filter then goes like this. Again, we step through this coupled kernel, which should have the correct marginals. We compute the MLMC Kalman gain estimator, which is a bit ugly. I'll show it on the next slide. And then we independently draw these perturbations on the noise, and we compute these guys, and we compute these guys here for the coarse and the fine. And okay, so that's all right. So that's how that works. We iterate this process, and so the multi-level for the Kalman filter is coming in through the estimate of the gain, and the same multi-level gain is used on all levels, all pairs of levels. And so what does the multi-level gain look like? It looks like this. So this is just one way that we can get around the fact that this is not positive. So you have this multi-level covariance estimator. This thing is convergent. It has the right rates and everything, but this covariance is not guaranteed to be positive. If it was positive, then we would be able to compute this inverse here. Since it's not, the way that we deal with that is by just truncating in this term, but not over here, the negative eigenvectors. So that's one way to get around that. And this is just the multi-level estimator of the second moment, differences of the second moment, fine and coarse, and then first moments squared. So for the multi-level ensemble Kalman filter, we get this multi-level empirical measure, which converges to the level L limiting measure, which is not the filter at level L, but is this mean field ensemble Kalman filter. So if the coefficients of the SD are globally Lipschitz, the initial condition is an LP for all P, and beta is bigger than zeta, then for appropriate phi and for epsilon positive, we can choose L and NL so that we get this type of convergence. So that we get LP now error bounded of size epsilon with a cost of log epsilon to the 2n epsilon minus 2. So this guy, we are not happy about that guy, and we also, numerical simulations indicate that we don't have that guy. These are the numerical simulations. Oh, this is swapped. Sometimes we like to draw the error like this, so in cost in terms of error. And here then you see the ensemble Kalman filter decaying more slowly, and the multi-level ensemble Kalman filter decaying like cost to the minus 1/2. Yeah, so multi-level particle filter can perform asymptotically as well as MLMC. We have this reduction in error rate, with this reduction in strong error. But still the cost epsilon can be the same as sampling a scalar random variable. We're able to preserve the rate with particle MCMC, that I will talk about on Friday. We have this, what we believe is spurious independent logarithmic penalty for MLE and KF. We also looked at MLE and KF for spatial models recently, and in fact, it may be possible with alternative couplings to get rid of this pesky reduction as well. So these are those papers again. Oops. Well, it's on arXiv, but it's also published now in SMC. Both are SMC. That's the SMC samplers from the previous and the one with normalizing constants. And I showed you the references already, so thanks. Sorry, I guess we're a little bit late, so yeah. Mm. Oh, no.
But even for some class of diffusion coefficients with risk, people don't understand that yet.
You're talking about this guy here. So how does that relate to the filtering distribution in general?
Is there some characterization?
It's so basically I call that, and I have a paper in CISC where I look at that, but I'm not able to say anything specific about that. So it's basically you can say something about convergence of ENKF to this process, and then I call that thing the Gaussian bias. Because if the limiting thing is Gaussian, if you're linear Gaussian, you have a common filter, you have convergence, and this thing is the same as that. Outside of that case, the best you can say is basically how close to Gaussian are you. So if you have, so you're sort of, observing very frequently, and or you have, a mildly nonlinear forward map from one time to the next. You have something there. Yeah. Otherwise, I mean, one argument that people like to make is that at least for a single step, this limiting thing would give you the minimum mean square error estimator over all linear functions of y, of that observation. So, and that may also hold recursively over time. I'm not aware of that being proven. So.
Okay,